Okay, this is part 2 for section 2.2 pre-calc classes. We are again going off of our equation, our power function, k times x to the a. For all the a's that are greater than 0, just talking about some language here that you guys are going to see. F of x, we can say that f of x varies directly as the eighth power of x. Now this is for exponents that are positive. Or we can say that f of x is directly proportional. Both of these phrases mean the same thing. Okay? So really, if you see varies or proportional, you can assume that the exponents are positive. Now for negative powers, so when a is negative, we say f of x varies inversely as the eighth power of x. Or f of x is inversely proportional. So really the key word is inversely. If you see inversely, that tells you right away that your exponent's going to be negative. If you don't see inversely in the problem, then you're going to have a positive exponent. Now, they're going to give us some functions here. We're going to determine the power, constant of variation, and then we're going to describe it. The first formula should be familiar to all of you. It is circumference. Okay, C of r, that means r is the variable, right there, equals 2 pi r. Now the power, well, r is the variable. There is no exponent, so we assume there to be a 1. So the power is 1. And the constant of variation is 2 pi. The description, okay, we would write this way. The circumference varies, that's the word varies, directly as the radius. Okay, so that's what we say. The circumference varies directly as the radius. Now, obviously we're using that statement right there. Okay, notice there's no square of the radius, because up here it says varies directly as the eighth power. Well, there is no power. Well, there is, but it's a 1. So you don't say the first power. You just say as the radius. Area formulas below that. A of r equals pi r squared. Again, r is our variable. This time the power is 2. Our constant of variation is pi. Now, when we write the description here, I'm going to use the second statement just to show you. So the area is directly proportional to the square of the radius. Notice I use the square of the radius because the radius is being squared. Okay, so whatever the exponent is, you kind of have to indicate, what that is. Now, that's the first two. Let's look at the next two. All right. Now, these formulas may not be as familiar to you. One is a physics one, one's a chemistry one. Not a big deal. Okay. I'm not asking you to memorize those formulas. But for this one, f of d equals k over d squared. Now, d is the variable. Okay, d is the variable. Since d is the variable, the exponent is not 2. And the reason why is because that d is in the denominator. The 2 is in the denominator, so the power is actually negative 2. And the constant of variation is k. So since the variable is, since the exponent is negative, the power is negative, this is how we're going to describe it. F stands for force. Insert Star Wars joke here. The force varies inversely, that's a V, inversely as the distance. Okay, D stands for distance. The fact that F is force and D is distance, fine. But you get the idea with the negative 2 power, means we have a varies inversely situation. Okay? And I should say, excuse me, it varies inversely as the square of the distance, because we are squaring the distance. Okay? Now if you look at the next one, okay, v of p equals k over p. Now p is our variable. Okay, now again, p is in the denominator. So the exponent, or the power, isn't 1, it's -1. And again, k is our constant of variation because we just don't know it. So this is more of a chemistry one. V stands for volume. So the volume is, now I'll use the other phrase, is is inversely proportional as the pressure. Okay? Now, you don't have to, I mean, again, the volume being V and the pressure being P, I'm not worried about the fact that you know what the variables are for this. But again, inversely, the variables, or the, excuse me, again, the power is negative, we use the word inversely. Okay? Now, if we go backwards, so if they give us the description, can we come up with the formula? Well, the period of time t for the full swing of a pendulum varies as the square root of the pendulum's length L. Okay, well, period of time t, okay, so that's t equals, it varies. Now again, it doesn't say directly or inversely. Like we said before, if it says just varies, that means we're automatically going to have a positive power. Now, it says the square root of the pendulum's length L. Now, I don't know what the constant of variation is. I don't know that. So it's just K, because I don't know. Times the square root of L. L is the pendulum's length. But again, square root means what power? Square root means 1/2 power. And our constant of variation is K. Same thing down here. The volume V, so we're going to have a V equals situation. A circular cylinder with fixed height is proportional to the square of its radius. Now, the fact that the height is fixed means I don't care about it. Okay? The height is fixed, that doesn't factor into anything. Proportional to the square of its radius. Proportional, again, no inversely here, so we're going to do, it's going to be a positive exponent. Square of the radius. So I don't know my constant of variation. I don't, so I just put K, square of the radius, R squared. So our power is 2, and our constant of variation is K. Alright, last one. It said it was going to be a shorter video. That's true. Okay, so we have a table here, okay, talking about noted astronomer Johannes Kepler. He developed 3 laws of planetary motion that are used to this day. Kepler's third law states that the square of the period of orbit t, this is the time required for one full revolution around the sun, for each planet is proportional to the cube of its average distance from the sun. Then they give you the table. Okay, the distances are given in millions of kilometers or gigameters, which is what the GM stands for. It says use the data in the table to obtain a power function model for orbital period as a function of average distance from the sun. Then use the model to predict the orbital period for Neptune, which is 4,497 gigameters from the sun on average. Okay, first things first. First thing you're going to do, stat. Edit. Okay, here's your L1, here's your L2. Alright. Then, so after you plug in your information, okay, we're going to go stat And then we're going to arrow over to calc. All right. Now, we're used to doing the linreg, quadreg, all that stuff. And it's on that menu. You are going to go all the way down to where it says power reg. What that does is that gives us our power function. Okay? So the linear regression gives us the equation of a line. Our quadratic regression gives us a quadratic, an x squared. The power regression is going to tell us the power function for this table. Okay? Which should tell you that y equals 0.20 x to the 1.5. Okay? Now, how can I write that? Or rewrite it? So I have 0.20 x to the 3 halves. Because 1.5 and 3 halves are the same, so I change it to a fractional exponent. If I changed it to radical form, the 2 on the bottom is the root. So I have a square root of x to the 3rd power. Okay? Now, the y in this case, that would be t. So if you really wanted to be specific about it, this would be t. Alright? And then our average distance we could still just call it x. So now that I have my function, okay, now you could use any one of these 3. I'm just showing you the 3 different ways you could write it. Okay? This is just the 3 different ways you could write it. I would accept any of those. Okay, part 2. Now we're going to use the model we just found to predict the orbital period for Neptune, which is 4,497 gigameters from the Sun on average. So, really, the easiest way to do it is probably just to plug it in here. So t equals 0.20 times 4,497 to the 1.5 power. Okay? So, you figure that out, and you should get, I believe, 60,313 days. Okay? Now, I'd be very interested, guys, convert that to years. And we'll talk about that in class. How many years that is. Okay? Now, remember, this is how long it takes to do one full revolution around the Sun. Just one full revolution. Okay? So it takes 60,313 days for the Sun, or for Neptune to revolve around the Sun. Kind of interesting. So that's part 2.